Hello everyone, we are Group22. Today we present our final report, Fuzzle PID and PID control of three-phase brushless DC motor. This part is the team's contribution. The main tasks include the derivation of mathematical modules, the design of control modules, the design of power and PWM modules, as well as optimization, simulation debugging, testing, and result analysis.
So let's start from part 1, background and motivation. Three-phase brushless DC motors are widely used in EV drives, drones, robotics, and household appliances because they are high efficiency, high power density, and low maintenance. However, in practice, the motor faces sudden load changes and speed commands, and its dynamics are nonlinear and strongly composed. A fixed-gain classical PID controller can overshoot, oscillate, or recover slowly when the operating point changes. So our motivation is we want faster speed tracking and better disturbance rejection without having to return gains for every new condition. So the goal of our project is to build a closed-loop BLDC control module with a speed loop and a current loop. Then implement two different speed controllers, a classical PID and a fuzzy PID. Then we test both controllers in 3 scenarios: startup, load disturbance, and deceleration. We compare them using quantitative metrics like overshoot, settling time, steady state error, and
In this part, I built a mathematical model for surface-mounted BLDC under some idealizing assumptions. We assumed sinusoidal back EMF and a symmetric three-phase stator, identical phase resistance and balanced self-inductance. Magnetic duration and higher-order harmonics are neglected. On this page, we will start from the three-phase stationary coordinate system to establish the electrical model of the BLDC. On the left is the voltage equation, and on the right is the flux linkage equation. Under the assumption of symmetrical three-phase operation and ignoring duration and harmonics, we use the Clark's transformation to project the three-phase model into the alpha-beta stationary coordinate system. In the alpha-beta coordinate system, the voltage equation and the flux linkage equations are obtained, and thus the electromagnetic torque is derived. Based on this alpha-beta model, in the next step, we will perform the Park transformation to enter the rotor synchronous DQ coordinate system. This part, I will discuss the mathematical model of brushless DC motor in two-phase rotating DQ coordinate system. These two pages present the Park transformation and the final model in the DQ rotational coordinate system. By applying the Park transformation, the three-phase quantity are mapped onto the D-axis, which is aligned with the rotor flux, and the Q-axis, which is orthogonal to it. This transforms the coupled three-phase equations into two compact first-order equations. In the DQ coordinate system, we obtain the relationship between voltage, flux, and current is only coupled within the X and includes cross terms related to the electrical angular velocity, and the electric magnetic torque can be expressed as flux plus the orthogonal components of the current. For a surface-mounted BLDC, LD approximately equals LQ. The torque is approximately 0, and the torque is essentially determined only by IQ. The control strategy is to keep ID near 0 and use IQ for the torque productions and speed regulation.
Hello everyone, I'm Suzhou Li. I'm introduce our module. This module adopts a FOC structure of fuzzy PID speed over outer loop with PI current inner loop. This through park decoupling as PWM drives the inverter and the motor. Turning time measurements of ABC and omega m is used to form a closed loop, and the overshoot, turning time, and anti-disturbance performance are verified entering loading and declaration steps test. On the upper left of the is the speed control module. In the middle is the current loop module. On the right side are the coordinate and the power stage, which includes the cloud module, the SV PWM module, and the plant, which is three-phase inverter bridge and the motor. On the far right is the control object and measurement. And this page shows the complete system of our structure. Um, this page shows the specific structural diagrams of the speed loop and the current loop.
Now let's start from part 5, parameter settings. As PDF shows, first we need to determine the motor parameters under the simulation conditions. Then, based on the electrical time constant, determine the target bandwidth of the current loop, and select the lower bandwidth of the speed loop. The current loop PI parameters, and the speed loop parameters were calculated as PDF shows. The advantage of this configuration is that the current loop responds quickly and has low coupling, while the speed loop is more stable. This ensures that both the overall dynamic and steady rate performance can be achieved. The following part is the analysis of the simulation results. As the figure shows, it presents the three-phase stator current, showing the complete process from no-load to loading and then to deceleration. The phase current rapidly establishes and reverses during the step to provide the required electromagnetic torque. The steady state maintains a balanced three-phase sine wave, with the frequency and amplitude corresponding to the changes in speed and load. These two graphs represent the current along the d-axis and the current along the q-axis. The d-axis current should be close to zero for a surface-mounted BLDC. In our results, both controllers keep ID around zero, and the faster PID shows smaller spikes and a faster return at both the load step and the speed step down. The q-axis current is the torch current. When we apply load at 0.3 seconds, IQ steps up to a higher level. When we command deceleration at 0.6 seconds, IQ briefly goes negative to produce breaking torture. Compare with classical PID, the faster PID gives faster rise and less oscillation, which translates to quicker torture buildup and better disturbance rejection. This figure shows the electromagnetic torture. For a surface-mounted BLDC, according to the previous derivation, torture mainly follows the IQ command. At 0.3 seconds, when the load is applied, both controllers raise torture to a higher level, but the fuzzy PID builds torture faster and with less ring. At 0.6 seconds, with the speed step down, torture briefly goes negative to break the rotor. Again, the fuzzy controller settles quicker. Steady state torture is the same, so the improvement is in transient quality, smaller overshoot and shorter settling time. And this slide compares the speed response. The red dashed line is the reference. At startup, classical PID shows larger overshoot and oscillation, while the fuzzy PID settles faster. When a load step is applied at 0.3 seconds, the fuzzy controller limits the speed dip and recovers more quickly. For the speed step down at 0.6 seconds, it also produces a smaller undershoot and a shorter settling time. Although, for the PID improves transit quality in all scenarios with the same steady-state accuracy.
To conclude, a cursor speed rises to 1000 revolutions per minute, a load step at t equals 0.3 seconds, and the speed drop to 800 revolutions per minute. Fado PID consistently shows smaller overshoot, faster settling, and quicker disturbance recovery than classical PID, while steady-state errors are comparable. This indicates the Fado supervisor adapts the gains effectively under transients and load changes, giving better robustness without extra steady-state cost. If possible, future work will include anti-wind-up refinements and hardware in the loop tests. Thank you for your attention.